In this video, we will try to derive the formula for the number of microstates for MB statistics, FD statistics, and the Bose-Einstein statistics. For MB statistics, which is the Maxwell-Boltzmann statistics, the formula for number of microstates is n factorial in this multiplication of uh, gi power ni divided by ni factorial. I will explain what are they one by one. N is the total number of particles. Gi is the degeneracy of ith level, and Ni is the number of particles in the ith level. So basically n1 plus n2 plus n3, which is the summation of all the particles in each level, should be n, or summation ni should be n. Now just to make things clear, let's do a little bit permutation combinations. Let's say there are uh, some n objects, n identical objects, and like this n circles, and let's say r triangles. Okay, so how many ways can these be arranged? The total number of objects is n plus r, so n plus r factorial is the total number of uh, ways these can be arranged. And since n objects are identical, so we will divide it by n factorial, and since r objects are identical, we will again divide it by r factorial. Similarly, if n1 particles are identical, n2 particles are identical, n3 particles are identical, and total number of particles is n, which is n1 plus n2 plus all of that, then the total number of arrangements we can make is in capital N factorial divided by n1 factorial, n2 factorial, n3 factorial, and all that. Okay, so now let's move on to the MB statistics. In MB statistics, what are the conditions? It means that in MB statistics, the particles are distinguishable, and any particle can occupy any state, and each state can be occupied by any number of particles. Okay, now let's consider energy levels like this. This is, let's say, E1, E2, E3, and it has E3 level has degeneracy G3. Let's say there are more energy levels like this. E2 has degeneracy G2, and E1 has degeneracy G1. And in this level, correspondingly, n3 number of particles are there, n2 number of particles, and n1 number of particles. Okay, so and total particles is n. Okay, so first of all, in how many ways we can divide n particles in these levels? In it should be n factorial divided by n1 factorial, n2 factorial, and n3 factorial dot dot dot. Okay, which is n factorial pi I. This is just a short form of this. This means basically ni, this pi ni means n1 into n2 to n3. Okay, so ni factorial is nothing but ni factorial is n1 factorial into n2 factorial and all that. Okay, okay, so this is the number of particles. So this is the number of ways we can divide n particles, capital N particles, in a group which has n1 particles, another group which has n2 particles, another group which has n3 particles. Okay, and now each energy level E1 has degeneracy G1. So we can divide this n1 small n1 number of particles in this G1 levels. What is degeneracy means? This E1 level, this level can be divided into G1 number of levels. All of them has energy E1. Okay, so and there are n1 particles to be divided in this G1 level, right? So again, let's move to a simple example. There are let's say five boxes and uh, three balls. Okay, in how many ways we can divide these three balls in this five levels? If five boxes, we'll take first box, the first ball. How many ways we can arrange this? Five. And and let's there are three balls, right? Ball one, ball two, ball two. Ball one can be divided into five ways. Ball two can be divided into again five ways, and ball 3 also can be divided into again 5 ways. So it's 5 cube. So similarly, this the number of ways this n1 particles can be divided is g1 to the power n1. Okay, let's rub this one. So total number of arrangements is n factorial divided by pi I n I factorial into g1 power n1. For energy level E2 also, g1 power n2 into g2 power n2 and g3 power n3 and so on. So we can write this part in the form of pi I gi ni. So overall we'll write this as n factorial pi I. This will write together. So gi ni by ni factorial. Okay, so this is the number of ways we can uh, arrange these particles in MB according to MB statistics. Now let's move on to FD statistics. The Fermi-Dirac statistics. Now, what is the properties of the fermions? Which is that one fermion can occupy one energy level only. This is the Pauli's exclusion principle. Exclusion principle. Pauli's exclusion principle. Okay, so let's consider energy levels E1 G1 N1, E2 G2 N2, E3 G3 N3, and so on, which is energy E3 has degeneracy G3, and number of particles in there is N3. Okay, so number of ways we can arrange is for energy level E1. Okay, and so the number of ways uh, uh, we can select or arranged N1 particles in G1 levels is simply N1 CG1, the basic combination. We can select any, let's say there are n objects, n identical objects. We want to select identical, or it might not be identical also. We want to select any there are n such objects, and we want to select any r out of these. So we can do it in NCR ways and NCR ways. So here the total number of uh, sorry, this should be G1 C N1, because there are total uh, G1 levels G1 levels here are G1 levels G1, sorry, and there are N1 number of particles to be distributed. So G1 C N1, and the condition is G1 should always be greater than equals to N1, because if there are less number of levels than the number of particles, it cannot be distributed. Okay, not all of the particles will be able to distribute in in those levels, because at one time there should be only one particle at each level, right? So let me rub this, and for the second level also same thing, G2 CN2, again G3 CN3, and this will go on. So G1 factorial in basically this thing in factorial G1 minus N1 factorial, G2 factorial into factorial G2 minus N2 factorial. This will go on. So in short we can write pi I Gi factorial Ni factorial Gi minus Ni factorial, or pi I Gi Cni factorial. Or maybe we cannot write that. Just love this one. So basically this is the formula uh, for FD. Okay, now let's move to the next part, which is uh, the Bose-Einstein statistics. What are the conditions? E particles are indistinguishable, which means all the particles, if you swap two particles, both will be the same state. Let's say there's E1 and there's E2, then particle A, and if there's one particle here and another particle here, and if both swap places, we cannot distinguish this state from this state. Basically these two will be same will be the same state. Okay, and and each there is no restriction, there's no restriction in the number of particles in each state. Okay, now how would you count the number of microstates, number of ways it can be arranged? Okay, this is a bit difficult, so please concentrate. Okay, let's say there are, just listen to me, yeah, everything will make sense after a while. Look, there are, let's say, n circles, and there are r minus 1 bars. Okay, so the number of ways these can be distributed is n plus r minus 1 factorial. As I said, for the MB statistics, the total number of particles is n plus r minus 1 divided by n factorial into r minus 1 factorial, because n objects are identical and r minus 1 objects are identical. So this is basically n plus r minus 1 c r minus 1, right? Just a minute, let me write it again. N plus r minus 1 c r minus 1. Okay, okay, okay. Now, now let's let's consider this. Let's consider there are 5 boxes. 1 2 3 4 5. So let's ignore these bound. So how many boundaries are there? 1 2 3 4 5 and 6. Let's ignore these extreme boundaries. So how many boundaries are there? 1 2 3 and 4, which means if there are 5 boxes, there are 4 boundaries. Okay, 4 boundaries ignoring the extreme ones. So if there are are there are k boxes, there should be k minus 1 boundaries. So similarly, if we now replace the box with an energy level. Okay, so if there are energy levels eh, g energy levels, then we can say there are g minus 1 boundaries. Okay, just accept the fact. Okay, everything will make sense. And if there are n n n particles, right? So we want to put n particles in g number of boxes. Let's consider these uh, as these energy levels as box. Okay, so g minus 1 boundaries. So now let's again go back to this one. How what does it mean to count the number of ways? We can say arrange these objects like this. So this becomes one box, this becomes one box, this becomes another box, this becomes another box. So in this box there are 2 objects, there are one object, there are 0 objects, and there are 2 objects, and so on. So similarly, so again replace the box with an energy level. So in the first energy level there are two particles. Second energy level there are one particle. In the third level there aren't any particles. Basically this is what we wanted to count, right? We wanted to count if there are g number of energy levels and n particles, what is the number of ways. So if there are g levels and n particles in each level, then what is the number of ways? N plus g minus 1 factorial c, sorry, not factorial, g minus 1, right? So so so, so again back to that same setup. E1 g1 n1, E2 g2 n2. So what is the total number of ways? this is Bose BE, is Ni plus Gi minus 1 C Gi minus 1 into this is G1, sorry, G1 for the first level. Similarly, for the second level, it will be G2 minus 1 C G2 minus 1, and so on. So we can write this as pi I N1 plus G1 minus 1 C G1 G, this would be I Gi minus 1, which is again pi I in Ni plus Gi minus 1 factorial divided by Gi minus 1 factorial into Ni factorial. This is the answer. Okay, so let's do some questions. There are total 10 questions here, so let's start. The number of distinct ways of placing 4 indistinguishable particles into 5 distinguishable box. Let now there are 4 indistinguishable particles, which means we can treat this as a problem in FT, sorry, MB statistics, sorry, FT statistics or Bose-Einstein statistics, right? Now, since there's no restriction in the number of particles in each state, so we can say we can treat it as the Bose-Einstein statistics and not FT statistics. Okay, so in Bose-Einstein statistics, which is what is the number of ways we can arrange? BE is Ni, the multiplication of Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. Okay, so now since there's only one state, we can say n plus G minus 1 factorial and factorial G minus 1 factorial. Okay, so what is the number of particles, which it's 4, and number of boxes, which is comparable to the number of energy states, which is 5 minus 1 and 4 factorial, and again 5 minus 1 factorial, which is 4 factorial. This will come out to be 70 ways. This is the answer. Okay, now let's go to the next question. Just two There's two identical particles uh, non-interacting. Four He2 atoms are distributed among 4 different non-degenerate energy levels. Okay, four. So there's 4 He2. There are two particles and 4 energy states. Okay, the probability that they occupy different energy level is P. Probability of different energy levels is P. And for for 3 He2 atoms, for again there are such two particles, and there are again 4 energy levels, 4 levels, and the probability of that they occupy energy level Q is in different energy level is Q, is different energy level is Q. Okay, now both of these look kind of the same. Here two particles, here two particles, here 4 particles, 4 levels, here 4 levels, here two, but both are actually different. This has 2 electrons, 2 protons, and 2 neutrons, which means 6 spin half particles, which means this will act as a boson, which is integer spin particles. And this has 2 protons, 1 neutron, and 2 electrons. So this has 5 spin half particles, which means it will act as a fermion. This will obey B statistics, and this will obey FT statistics. Okay, now let's go try for 4He2 plus, which will obey the p statistics. So number of ways is n plus g minus 1 factorial n factorial into g minus 1 factorial, which means n is 2 plus g is 4 minus 1 factorial, 2 factorial into 3 factorial, right? 6, this is 5 factorial into 3 factorial into 2 factorial. So 5 into 4 is divided by 2, which is 5, right? This is okay. This is this should be, or am I making a mistake? 5 into uh, 6 minus 1, 5 factorial. This should be 2. Sorry, this is 10. 10 number of ways, 10 ways in which this 4 uh, number of ways number of ways for 2 particles can be distributed in 4 levels. Okay, according to B statistics. Now what is small p? Small p is the number of ways is the probability that these 2 particles is distributed in different levels. There are 4 levels, and there are 2 particles. So how many ways it can be distributed? It's just NCR, which is 4 levels, CR, which is 2. Uh, what is this basically? The number of ways we can pick any of the 2 levels among these 4 levels, and we can again distribute that. Since both are indistinguishable, 4C2 is just fine. Then this will be 4 factorial, 2 factorial into again 2 factorial, which is 4 into 3 into 2 into 1, 2 into 2, which is 6. So P, this is not, sorry, this is the this divided by the total number of ways is the uh, is the is small p. Again, again, small p is the probability, which means what is probability? Probability is number of favorable ways or possibilities divided by the total possibilities. Number of favorable ways is 4C2 divided by the total number of possibilities, which is again 10. 10. So 6 divided by 10, 0.6. Okay. Now what is small q? Small q, small q is for the 3He2, right? 3He2 will obey FD statistics. Okay. So what is the total number of ways? It will be distributed in different levels. It's again what is the FD? This is 4C2, which is 6, as we did earlier. Now what is the total number of favorable ways? Number of favorable ways, which is different levels. We know that in FD statistics it has to be in different levels. So again it's 4C2, it's 6. So small q is 1. Now, now again we could have just said 1 without any calculation, because in FD statistics anyways the levels will be distributed in different levels. It always has to be the case. So q is 1, so p by q is 0.6 divided by 1, which is 0.6. Okay, let's start question 3. A system of n non-interacting particles, non-interacting and distinguishable particles of spin 1 is in thermodynamic equilibrium. Now remember, these are distinguishable particles. Just don't see spin and consider it as indistinguishable particles. So FD or Bose-Einstein statistics cannot be applied here. Okay, so there are n and now spin 1 particles. So spin 1 particles, S is 1. which means it can take three energies, which is why 2s plus 1 energies it can take. So 2 into 1 plus 1, it can take 3 energy possible energy states. Okay, so there are three energy states, three energy now again, since there is distinguishable and non-interacting, we can model this as this, let's say there's a lattice points, and uh, the spins are are fixed, uh, are these spins are fixed at these lattice points, so we can easily figure out which one is what. Okay, so for this one, let's say for the first particle, there are three possible energy states. Similarly for the second, similarly for the third particle also. So and this particle, this spin can be arranged in how many ways? Three ways, because there are uh, particles, three energy levels and one uh, spin. So there are basically three possible states it can have, right? So three ways. For this one also three ways, so multiplied by 3, and for this one also 3. So this will keep on continuing till for all the particles. How many particles are there? N particles. So 3 to the power n number of ways it we can this system can have 3 to the power n number of microstates. So and s, we know s is kb ln omega. So kb ln 3 to the power n, this n will come outside in kb ln 3. This is the answer. Now let's go to the next question, which is fourth question. Now look at this question: linear collection of an independent spin, which means they are non-interacting, and the fixed at fixed location, which means they are distinguishable. Now, if we compare this question with the earlier one, with the last one, we'll see that both questions are exactly the same, except that it has spin 1 and this one has spin half. So number of total ways this can be arranged is number of energy levels a spin half particle can have is 2s plus 1, which is 2 into half plus 1, which is 2 levels. Okay, so again for by the same method, number of microstates would be 2 to the power n. Again, s is kb ln omega, which is kb ln 2 to the power n in kb ln 2. Again, so D is the answer. Question 4, we need to find the density of states in 2D as a function of energy. We'll do these kind of questions later, but let's do it for now. Now, what is the proportionality? How does the what is the formula for density of states? It's proportional to the phase space volume. Okay, rest of it is in that doesn't have energy proportionality, so we'll put it in constant. Okay, so what is phase space volume? It's the momentum space volume multiplied by the configuration space volume, right? So what is momentum space volume? In 2D it's basically area, right? In 2D volume means area. Px py, if we draw a circle and a shell around it, I mean a ring around it, with width being dp and radius is p. So what is this area? This area is 2 pi p dp, right? Now p is what? Momentum, sorry, 2 root 2 eme, and dp is what? 1 root 2 m half into this. Okay, so what is uh, the any, what is any? It's 2 pi pdp, as we said. proportional to 2 pi pdp. So 2 pi multiplied by root 2 m e multiplied by this will become root m by 2 e to the power half. This will get cancelled out, so we'll get e to the power 0, which means there's no energy dependence, right? So Ne doesn't depend on energy, okay, which is same as writing e to the power 0, which means our option C is correct, this one. Okay, now let's do this question. Consider a system of n non-interacting particles, which means independent, right? And then particles, spin half particles, each having a magnetic moment mu is in magnetic field B. Okay, spin half particles, right? So it can be either parallel or anti-parallel to the magnetic field. Spin half particles, there's basically two energy configurations. Y2 2s plus 1, which is 2 into half plus 1, which is 2. Okay, in the when B magnetic field is applied, it will either be parallel to the magnetic field or anti-parallel to the magnetic field. Okay, spin magnetic field. Okay, in this case the energy would be minus mu dot B, which is minus mu B, right? Cos theta is 0, cos theta is 0, basically cos theta is 1, and here it will be minus mu naught B, which is minus mu B cos 180, which is plus mu B. Okay, these are the energies, which means it will be arranged in two uh, two it can basically either have minus mu b energy or plus mu b energy. Now there are n particles. Let's say n plus of them are in spin in upspin, and n minus are in downspin. So and total energy is given E here. It's the total energy. So E is n plus in spin half in parallel. So uh, let's say it's spin down, it, just for easy calculations. Okay, so E is mu b n plus n n plus will have energy mu b, and plus minus mu b for n minus particles, n minus spins. So mu b n plus minus n minus, right? And we know, and obviously n should be n plus plus n minus. So using this we will get n plus is e half n minus e by mu b, and n minus is half n plus e by mu b. Okay, just use these two equations, just put n plus is n minus n minus and put it here, you will get this one. Okay, just eliminate capital N, this one. Okay, no, sorry, not eliminate, while finding n plus eliminate n minus, and while finding n minus eliminate n plus. Okay, you will get this one. So there's once this is plus mu b and this is minus mu b. Okay, each spin can be either in upspin or downspin. It has two possibilities. This also has two possibilities. All of them have two possibilities of energy. So uh, so we can say we want to say that for here two possibilities, for here two possibilities, so here two possibilities, so 2 to the power n. But this cannot be used here, because we need to make sure that the total energy is capital E. right? Total energy is fixed always. We cannot use this, right? So we know that out of n out of n plus is in spin is is in the higher energy level, which is spin down, right? This is in the higher energy level. So what is the total number of ways it can be done? It's the total number of ways is if there were no to arrange this in uh, so the number of ways we can divide n particles is in capital N factorial, and out of them n plus of them are in the upper state, and n minus of them are in the lower states. So n plus of them are the same, right? So we'll divide it by n plus factorial, and we'll divide it by again the n minus factorial, because n plus of them out of n are similar, and n minus of them are similar out of n factorial, right? So we'll just put it put the values, which means this will be half n minus e minus mu b factorial into half n plus e by mu b factorial. This is the answer, which means option A is the answer. Okay. As I said in my earlier question, the density of states in 2D is uh, not doesn't depend on energy, which is e to the power 0, which means is n is 0, sorry, and this is given in 2D. So density of states, it doesn't depend on energy, so e to the power 0. Okay, we find, this is homework, find g, how g depends on e in 2D and 3D, sorry, 1D and 3D also. Okay, now let's move to the next question, which is this one. The entropy S of a system of n spins which may align either in upward or downward direction is given by this. Here is Kb is the Boltzmann constant. The probability of alignment in the upward direction is P. The value of P at which the entropy is maximum. So we'll just do del S del P is 0. This is the condition for maximum. This is the condition for extrema. In this case, we will get a maxima only. Okay, so just do the maths. This is, this should be like this. Okay, so if we differentiate, we'll get p 1 by p plus ln p into 1 plus 1 minus p divided by 1 minus p into minus 1 plus ln 1 minus p to minus 1. Okay, so this will get cancelled, this will get cancelled, this is 1, this will get cancelled, this is minus 1, 1 minus 1 will get cancelled, this equals to 0, right? So ln p plus the minus ln 1 minus p is 0. So ln p by 1 minus p is 0. So p1 minus p is e power 0, which is 1, right? So p equals to 1 minus p, 2p is 1, p is half. This is the answer. Okay, let's do this question. N atoms of an ideal gas are enclosed in a container of volume V. The volume of the container is changed to 4V. So V is changed to 4V, keeping the total energy constant. E is constant, the change in the entropy of the gas in terms of n kb ln 2. This is n kb ln 2. In units of n kb ln 2 means we need to find this coefficient in front of n kb ln 2. Okay, so we know S is kb ln omega, right? But we cannot use this formula because there's no way to find this omega. We'll use the other formula, which is dq by t, integration dq by t. Dq is what? It's again du plus p dv. Okay, du is 0 because total energy is constant. P by t dv integration. So p, we know pv equals to n kbt. So p by t is n kb by v. Okay, so we'll put that in that equation. So s is n kb by v dv. Okay, n kb dv by v. This is in case this goes from v to 4v. So ln v to 4v. Okay, so n kb ln 4. This is again n kb ln 2. Why this 4 we can write as 2 to the power 2. This 2 will go outside ln, so 2 n kb ln 2, right? So the coefficient we need to find is this 2. Answer is, this is the answer. Basically 2 is the answer to this question. Consider a system of 3 energy levels with energies 2, 0, 2e and 3e. Okay, uh, 2e and 3 with the respective degeneracies of 2 and 3. 4 bosons of spin 0 have to be accommodated in these levels such that the total energy of the system is 10e. Okay, so there are 4 bosons. Okay, so 0, 2e and 3e. Spin 0 means that the energy levels will have uh, will it won't be degenerate actually. So okay, so this has degeneracy 2, this has degeneracy 2, this has degeneracy of 3. Okay, let's say here's n1 particles, here's n2, and here's n3. Okay, so total energy is 10e total. Okay, so n1 into the energy which is 0 plus n2 into the energy 2e plus n3 into the energy of the energy level is should be 10e, right? And we all, so basically this will go to 0. 2 n2e plus n3 n3e is 10e. So 2 n2 plus 3 n3 is 10, and we know that n1 plus n2 plus n3 is 4 because it's given total number of particles is 4. So so n2 plus n3 is 10. The only way it's possible is that n2 is 3, then it will become 6, and now n2 is 2 and n3 is also 2. Only then this will go to 10, and remember n2 and n3 has to be integers. So put that here, we'll get n1 plus 2 plus 2 is 4, so n1 has to be 0. There cannot be any particle in this energy level, so that uh, the total energy of the system is 10. Okay, so the number of ways it can be done. Now look, these these are basically bosons, right? Bosons, spin zeros. So number of ways is, we know, pi I ni plus gi minus 1 ni factorial gi factorial minus 1. Okay, so the for this level is, it's 0 plus gi is again 1 minus 1, 0 factorial, 0 factorial. Okay, so this is basically uh, this whole term will be 1, right? For the second level, it's what is n2? N2 is 2 plus gi is 1 minus 1 factorial, 2 factorial, 0 factorial, into again 2 factor 2 plus 1 minus 1 factorial, 2 factorial, 0 factorial. Okay, so it's 2 factorial by 2 factorial into 2 factorial by 2 factorial. So it's one ways it can be done. So for this level, we know for Bose-Einstein statistics, the given these are bosons, and these are bosons given. So for the first energy level, we know let's write the general formula first. Ni plus gi minus 1 factorial divided by n factorial into gi minus 1 factorial, right? So for the first energy level, there are how many particles? N1, and N1 is what? 0 plus gi. Gi is what? 2 minus 1 factorial. Gi is 2. Okay, 0 factorial into 2 minus 1 factorial into, for the second part, second state, n2 is 2 plus the number, what is the degeneracy? 2 minus 1 factorial, right? So 2 factorial into 1 factorial into again 2 plus 2 minus 1 factorial, 2 factorial into 1 factorial. Sorry, it should be 3. Degeneracy is 3 for the third level. 2 plus 3 minus 1 factorial into by 2 factorial by, this is 3 minus 1, so 2 factorial. So this is 1, this is 4 minus 1 factorial, which means 3 factorial by 2 factorial into 5 minus 1, which is 4 factorial, divided by 2 factorial into 2 factorial, which is 4. So this is 3 into 4 factorial, which is 6. 4 factorial by 4, which is 6, and so this will be 18 days. Now consider two systems A and B, each having two distinguishable particles. A has two particles, B has two particles. Each particle can exist in states 0, 0, 1, 2 and 3 units. Okay, 0, 1, 2 and 3 units, 0, 1, 2 and 3 units with equal probability. The total energy of the combined system is 5 units. The total energy is 5 units. Okay, assuming that the system A has energy 3 units and B has 2 units, the entropy of the system is kb ln lambda. What is lambda, right? So entropy is, we know kb, it's kb ln omega, which is represented by lambda here. So we need to find the number of microstates. That's our answer, right? So there are two particles in A, right? So and here it's given that the total energy is 3 units. So how many ways it can be possible? Here the particle can be and here another particle, right? He- the second possibility is here and here. This is, let's say, P and Q. Okay, let's write it properly. Here it's P, here it's Q, or here it's P, here it's Q. So two possibilities here. Here it's P, here it's Q, here it's P, here it's Q. Okay, then so total four possibilities. Okay, now in system B, 0, 1, 2, 3, the total energy is 2 units. So the possibilities are P, Q, and P, Q, and P, Q. There are no other possibilities. P and Q, let's write here. So there are three possibilities total. Okay, so what is the total number of microstates? It's 4 into 3. Okay, so 12. So lambda is 12.